We know what a unit tangent vector is, but I want to introduce you to a couple more special unit vectors called the unit normal and the binormal vectors. The unit tangent vector is shown here in yellow, and it points in the direction of motion. The principal unit normal vector is blue, and this is orthogonal to our unit tangent vector. It points in the direction that the tangent vector is turning. We can calculate the principal unit normal vector simply by taking the derivative of the unit tangent vector and then normalizing that to be a unit vector. So we have these two special unit vectors, t and n, and we can cross the two together to find another special vector called the binormal vector. This vector is perpendicular to both the unit tangent vector and the principal unit normal vector. So we can find it simply by crossing t with n. Now t is a unit tangent vector, n is a normal principal unit vector. But what about b? If we're crossing those two together, is b also a unit vector? Well, it turns out it is. Remember that calculating the magnitude of a cross product can be interpreted as the magnitude of each of the vectors you're crossing times the angle between them. Turns out that the angle between t and n is pi over 2, so sine at theta would be 1. The magnitude of the unit tangent is 1. The magnitude of the unit normal is 1. So the result says that the magnitude of b, this binormal vector, is also 1, meaning it is a unit vector. These three vectors, t, n, and b, make up something that's called a TNB frame. There's actually a few different names for this moving frame. You can call it a Fernet frame of reference or a TNB frame. And basically what it does is it gives you a reference that's dependent upon your current position in time. Now, when we use our XYZ coordinate system, we anchor that to the origin. And if we're moving away from the origin, we're always describing our position and our motion relative to an anchored point in space. But this TNB frame allows us to take the coordinate system with us, and that's what you're seeing in this animation on the screen. These three vectors, the yellow, the blue, and the purple, they're orthogonal to each other, just like x, y, and z are. But they're allowed to move freely with the point that's moving along the curve. Notice that these three unit vectors are moving in space even though the x, y, z axes are fixed in one spot. And these vectors are moving along the curve. You can see the yellow unit tangent vector is pointing in the direction that we're moving along the curve. The blue vector is pointing in the direction that the yellow vector turns. And then the purple vector, the binormal vector, it's really describing a tilt, so to speak. And it's orthogonal to both the yellow and the blue vectors. So we have this new moving frame of reference called the TNB frame. To find a principal unit normal vector, all we need to do is find the unit tangent vector, calculate the derivative of it, find its magnitude, and plug it into our formula. Once we have t and n, we could then find b. So let's try an example here. We want to find the normal vector, the principal unit normal vector, and the binormal vector for the vector function r. Notice it's not asking for the unit tangent vector, but we absolutely have to find it to be able to find these other two vectors. So we'll start by calculating the unit tangent, which depends on the first derivative of r divided by its magnitude. So we need r prime, which looks like -4 sine t I hat minus 4 cosine t j hat. The magnitude of that derivative would be 16 sine squared t plus 16 cosine squared t inside of a square root, which simplifies to be root 16, or just 4 after we take the square root. That allows us to calculate the unit tangent vector. We take r prime and divide off the magnitude, so we get negative sine t I hat minus cosine t j hat. So the 4 in r prime divided off of the 4 in the magnitude of r prime. So we have our unit tangent vector. Now we want to find the unit normal. That says take the derivative of this unit tangent function we just found, which would be negative cosine t I hat plus sine t j hat. Then we need to find the magnitude of that, which would be cosine squared t plus sine squared t inside of a square root, which is equal to 1. Now, I want to pause for a second and tell you this is an unusual situation. Not always will the derivative of a unit tangent vector be 1. So sometimes the magnitude comes out to be 1 for the derivative of the unit tangent vector, but not always. So now we have enough information to calculate n, the principal unit normal, which would be the unit tangent vector divided by the magnitude, and in this case, they're actually equal to each other. Now we can find the binormal vector, which takes the cross product of t with n. Our 3 by 3 determinant matrix to calculate this. We can plug in our components for the tangent vector, which would be negative cosine t, positive sine t, 0, and then the unit normal, negative cosine t, sine t, 0, and then we take our cross product. In the I hat direction, we have 0 times sine t minus 0 times sine t. That's 0 I hat. In the j hat component, we have negative cosine t times 0 minus 0 times negative cosine t. That's another 0. And in the k hat component, we get negative cosine t times sine t minus sine t times negative cosine t, which that actually works out to be 0 as well. The binormal vector in this case is a 0 vector, and if that feels strange, it really shouldn't. If we look at r of t, it's a 2D function. We can't technically have the 0 vector as the binormal vector, but I'll tell you what's going on. This vector function r is actually a circle centered at the origin with a radius of 4. The minus sign in the j direction changes our vector function to travel clockwise instead of counterclockwise. The unit tangent vector at any point would maybe look like this white vector. The unit normal vector at any point is pointing inside of the circle. And then the binormal vector, we can't really see it, but technically it would be pointing either into or out of the page. We'd need to use the right-hand rule to figure that out. So we'd point in the direction of our unit tangent, curl our fingers to the unit normal, and we would see that the binormal is pointing into the page. And in order to represent a vector that's pointing into or out of the page, we use something that's a little antiquated. A point tells you that the vector is coming at you. You're looking at the point of an arrow. A cross tells you that the vector is going into the page because it looks like the cross feathers on an arrow from a bow and arrow. So in this case, we know that the binormal vector is pointing directly into the page to make this orthogonal 3D coordinate system. But we really don't need the binormal vector in a 2D case because it's a 2D case, not 3D. We have one more example here for finding n and b. It is worked out in the textbook, so I'll leave that as an activity for you to do on your own.